many changes in the climate throughout Earth's history, including dramatic shifts that we're currently causing ourselves. On the other hand, no previous changes have been quite like what we're doing right now. So here's a quick tour of some of the strangest and most consequential climate shifts in Earth's past, and why our current warming is unique. Let's start with Earth's long-term climate cycles. Over the past 540 million years, Earth's climate has generally alternated between two modes, greenhouse and icehouse. Greenhouse periods are warm and ice-free, while icehouse periods are cold and covered in ice. These cycles have been driven by long-term changes in Earth's orbit around the Sun and its axial tilt, known as milankovitch cycles, which occur over tens of thousands to hundreds of thousands of years. In general, the frequency of these cycles causes more frequent glacial and interglacial periods in the northern hemisphere. Meanwhile, the magnitude of the cycles causes more substantial shifts in global temperature and precipitation patterns, driving full-blown ice ages. The most recent ice age began about 115,000 years ago and ended about 14,500 years ago, at which point we entered the current warm period or Holocene epoch. These long-term cycles are superimposed on shorter-term natural climate variability related to volcanic activity, solar radiation, and the exchange of heat and matter between the ocean and the atmosphere. The sum total of these factors produces a complex tapestry of environmental change over time, and understanding how they interact is critical if we want to predict how Earth's climate will change in the future. One of the most remarkable episodes of past climate change is the Paleocene thermal maximum, or PETM, which occurred about 55 million years ago. During the PETM, Earth's average surface temperature rose by 5 to 8 degrees Celsius within 20,000 years. That's about twice as fast as the average rate of warming since the Industrial Revolution and 10 times faster than the current rate of warming. It was so hot that the Arctic was basically treeless and rainforest extended as far north as southern Greenland. What caused such rapid change? Well, the leading hypothesis is that the PETM was triggered by the sudden release of massive amounts of carbon. Where did all this carbon come from? One idea is that it was stored in methane hydrates on the seafloor, which were released into the water column and subsequently oxidized to carbon dioxide and water. Another idea is that the carbon came from volcanic eruptions, perhaps in conjunction with the opening of a new East Pacific hotspot, which would have caused massive outpourings of lava in what is now the western United States and Mexico. Whatever the cause, the PETM is thought to have lasted for 200,000 years, after which Earth's climate began to cool. During the Eocene epoch, the PETM was a relatively brief but intense pulse of warmth in an overall warming trend. But that wasn't true for every episode of global warming in the past. Some were actually ice ages. About 750 million years ago, Earth went through a period of intense glaciation known as Snowball Earth. According to one hypothesis, the entire planet was frozen solid, which seems pretty hard to imagine. How could Earth have been both frozen and had oceans? Apparently, there was still water on the surface, just in the form of ice. You might not even notice snow on Earth because it's constantly being replenished by melting ice. But if Earth were completely covered in ice, it would reflect most of the sunlight that hit it, which would cause temperatures to drop until eventually the entire planet was frozen solid. To get out of this situation, Earth would need to undergo a runaway greenhouse effect, like Venus, to melt all the ice and reabsorb carbon dioxide from the atmosphere back into the crust. Interestingly, the snowball Earth hypothesis predicts that the most severe episode of glaciation occurred when CO2 levels were at their lowest, below 50 parts per million. Today, the level is about 420 parts per million, and it wasn't just CO2 that was low. Oxygen levels were also extremely low during the snowball period, along with nitrogen and other gases we take for granted today. So Earth was essentially a frozen desert with a thin, toxic atmosphere. And while this was happening, life somehow managed to survive, probably in the deep sea. Eventually, conditions returned to normal and snowball Earth ended. However, another episode of extreme glaciation, known as the Cryogenian, began about 635 million years ago and lasted another 150 million years. Cryogenian is thought to have ended when supercontinent Rodinia broke apart, and the resulting tectonic activity released large amounts of CO2 and warmed the planet. As with the Petium though, the Cryogenian was a relatively brief period of intense cold in an overall cooling trend. Before the snowball Earth was undergoing something called the Great Oxidation Event. At first, Earth's atmosphere was devoid of oxygen, so much so that the early oceans were full of anaerobic organisms that generated energy without using oxygen. But around 2.5 billion years ago, photosynthetic cyanobacteria began producing oxygen as a byproduct, which filled the atmosphere and poisoned most of the anaerobic life in the oceans. As the oxygen-rich atmosphere became more and more stable, land, plants and animals gradually evolved, and Earth's oxygen levels have been high ever since. So there you have it, a whirlwind tour of Earth's most dramatic climate shifts. Now, you might be wondering, is our current warming just another instance of the same old, same old? Well, not exactly. For starters, no other period of warming was as rapid as ours, at least in the instrumental record, which goes back about 150 years. Even the 20th century alone saw an unprecedented rate of warming, as shown by the famous hockey stick graph published in 1999 by Michael Mann and colleagues. This graph compares the average temperature of the Northern Hemisphere over the past 1,000 years. For most of the past millennium, temperatures were relatively stable and oscillating around a long-term average. But starting around the 19th century, temperatures began to rise steadily, and by the end of the century, they were about 2 degrees above the average. This dramatic shift was largely driven by human activities, especially the combustion of fossil fuels, which doubled atmospheric CO2 levels from about 280 parts per million in 1800 to over 580 parts per million today. The burning of fossil fuels has also increased the concentrations of other greenhouse gases, such as methane, nitrous oxide, and fluorinated gases. What's more, our warming isn't just unprecedented in the instrumental record, but also in the context of Earth's natural climate variability. Research based on sediment deposits, tree rings, ice cores, corals, and other archives of past climates suggests that the current warming is unprecedented in at least the past 2,000 years. Although some studies have questioned the reliability of these data and models, the consensus among climate scientists is that nothing in the paleoclimatic record provides an analogue for what is happening today. In other words, we've never experienced anything quite like this before. So, what does this mean for the future? While past episodes of global warming and ice ages can teach us a lot about the processes that drive climate change, they can't tell us for sure how our current warming will play out. That said, by studying past climate shifts, we can better understand the range of possible outcomes and assess the potential impacts of different future scenarios. We can also gain insight into the resilience of Earth's systems and the capacity of life to adapt to change. Ultimately, understanding the lessons of the past is essential if we want to navigate the challenges of the future. So thanks for watching another episode. If you liked this video, be sure to watch this one on how bad things could get if we do uncontrolled global warming. And remember, if you sign up for a brilliant subscription, you'll get access to my course, which covers topics in science and mathematics, from algebra to astrophysics,